Okay, thank you. So, hello everyone. Today I would like to talk about MONI-k and how to rebuild it. Um, so, First I'm going to give an introduction, and then I'm going to talk why we're going to build MONI-k and talk about the up table and the print up method that we use building the MONI-k. So one of the very helpful methods in order to find MEMS is RIndex, which is built using the PFP technique. And the problem is that RIndex cannot find MEMS all by itself. So that's why MONI was implemented, which uses PFP to build our index and at the same time find the thresholds, and it will increase the MEM findings efficiency. And it contains the RLWT of the text, the suffix array, and the locally consistent SLP of the text. And K-MEMS are when in a pattern P with respect to the text, there are parts of that pattern, say from position I to J, that occurs in the text at least K times. So we can say that MEMS are kind of K-MEMS, where K is equal to 1. So our index cannot efficiently tell us what are the substrings that occur in the text. It can tell us the position of the pattern that occurs in the text, but it cannot talk about the substrings of the pattern. And MONI also cannot efficiently tell us anything about the substrings frequencies, other than the fact that they occur at least once. So it is not efficient to use MONI for finding K-MEMS, and it takes of m log n plus k log n time to find K-MEMS, which is dependent on k, and it's not efficient. So the other option is to use data structures such as compressed suffix tree or the bidirectional FM index, but the problem is that there are no efficient implementation of such data structures for very large data sets such as pangenomes. So MONI-k was introduced by Travis Gagey very recently in order to determine what are the substrings of a pattern that occur at least k desired time in a data set. And it is a generalization of MONI that lets us set the frequency threshold, and it uses O of R plus G space, where R is the number of run boundaries and G is the size of a balanced SLP. So its goal is to identify what are the substrings that, given a K, will appear in our data set. So for K-MEMS, if we consider the text T of size N and the BWT of position I in the text, there exists a subsequence of BWT of I that is from position J1 to JK of the BWT that are the only copies of I in the BWT of J1 to JK. And it means that there are at least K-MEMS in the text. And if this subsequence does not exist, then there are less than K copies of the part of the pattern, and therefore there are no K-MEMS. And for a given pattern, P of length M, for a boundary in the pattern, in order to check if the K-MEMS can be found in the text, that boundary in the pattern needs to be processed, and the BWT of the SQ until EQ must exist with a length of at least K. So MONI-k can be implemented building the BWT, the suffix array, the LCP array using the SDSL tools, and it will take of m log n time to find the k-max. So the first thing I'm going to talk about in building the MONI-k is the op table. And this is our input string for this example. And as we can see here, we have, this is not the op table, I'm going to talk about that later, but for now we have this suffix array by the LCP and the BWT, and these are the suffix arrays. And this is the length of the input, and R is the number of the runs. And this is now our op table. So the first column is the sorted suffix array entries sampled at the BWT run boundaries. So this column is built by starting from the BWT column. We can see that if we store the position of the actually value of SA of I in that run boundary, and in each of the run head, we store the SA of I value of it. And here, for example, we start from the first position, we keep this value 24, and then we keep the value of SA of I for the next run head, which is 23, and then we will skip 4, 11, 19, and then again for this run head, we will keep 21, and then 1 and 5, and so on. And then we will sort these values, and that's how we will have this column. So we have 14 we have 14 runs. So the length of our SA column is also 14. And next we have previous column, which is the previous entry in the suffix array I column. So for example, for the value of 0, 8 is the value of the suffix array on top of it, which is correct, 0 and then 8. For 1, its previous value is 13, which is here. And this is how the previous, this is what the previous column indicates. And the concept of phi function is worth to mention here, that the phi of SA of I is equal to SA of I minus 1. So actually here the value of the previous is the phi of the suffix array value here. So next we have the pointer column. So the LCP is exactly the same thing. And pointer is the column that shows the position of the row where the predecessor of the previous value exists in the SA column. So for example, here, the predecessor of 8, it says that it's in row 6, which is here. The predecessor of 13 should be 10, and that's where the pointer points it to as well. So it will map us to 7. For 22, it should go to 22 in row 11, which is exactly the same thing, and so on. Next, we have the permutation table, which is used to access the ith run boundary in the op table. So for example, this first value, which is 13, it means that the first run head here, its value is 24, and it will show that 13 is the row where 24 is stored. So next we have the second run, like the second value, we will go to the second run head in the BWT. Its suffix array value is 23, and 23 is stored in the 12, the row 12, and that's where it will map us in the suffix array table column. So this will help us to access the ith round boundary, which is later going to be useful in the printf method. So this is the printf method, and it takes two arguments I and k. I is the ith round boundary, and k is the exact k in MONI-k and k-mems, which will print the k suffix array and LCP values above the inverse permutation of the ith round boundary in the upper table. And upper table is this one, and upper table is this one, but I will mention it as the lower table so that we don't get confused. So yeah, so printf starts at the ith row in the lower table, and at the at first it starts with j being equal to the SA value right below a given run boundary, and it assigns up table that previous value plus j minus up table's suffix array value to j, which will change j's value to phi of j. So it's worth noting that for when j is right underneath the given run boundary, the value of up table the previous is the phi of j, because j is equal to the up table .sa, and this part would be equal to 0, but it will be useful when this is not the case and j is not equal to the SA value that is below the given run boundary, and it will have a non-zero value. So I would like to give an example here. So assume that I is equal to 3, and that means that looking to our perm column, we can count from the top 0, 1, 2, 3. The third run boundary has the suffix array of 5. So third run boundary is 0, 1, 2, 0, 1, 2, 3 here. So this is 6, and it in here we will map into the fourth row. Sorry, I went to here. So the perm column tells us to, for third run boundary, we need to map to the row 4 in the lower table, which is 6. So 6 is the exact value of the SA value of the third run boundary. So here we can see that j is equal to 6, and its up table, that previous value is 9. So if we want to, so this is actually indicating the phi of j. So for j equals to 6, phi of j is 9. And yeah, so this is the same thing in the formula, because j is equal to 6 and its suffix array value is also 6. This would be 0. But if you want to know, so here 6 is here, and the phi of 6 is 9, which is correct. And if we want to know what is the value on top of 9, we okay, so we can see the pointer value, which is 6, and it tells us to go to the row 6, which is here. So with j being 9 and the previous value being 20, and the suffix array value being 8, we will have 20 plus 9 minus 8, which will give us 21, and that is the exact suffix array value on top of 9. So this is actually how printf method works. And yeah, so after that, we will print j and the LCP value. And then there are two things I would like to mention in the code. So there is this inner loop that seems to be doing nothing, but the thing is that it is actually, so when the predecessor of j is further down, and we need to go down in order to reach the SA value that is the j's predecessor, we will use this inner loop in order to descend to that row. And another thing is that we have the printing at the end of the for loop. It's because if we do otherwise, then it will give us the k-1 values of the k values we wanted. And why we want it to start printing the k values starting from right above the wrong boundary and not including it. So this is the output of printf method. It recovers the whole suffix array. And in here we can see the other output of the method, which starts from the last boundary and prints the k elements above it. So here k is equal to 5, and we start from the last boundary, last round boundary here, actually the last row. So with respect to the run heads, we will go up, and we will have the 5 SA values and LCP values at each 5 outputs of printf results. So you can see here, for example, it goes from bottom to up, and it will print it top down. So it will go on, and at the end it will wrap around, and it finishes the whole suffix array value and the LCP values that we wanted. So if we build MONI-k using the PFP, it will take us linear time, even if you want to just change k, whereas using the phi function and the Nishimoto-Tabe theorem, we are guaranteed that we're not going to have so many flips through the rows, and it will take us less time of KR time. And as a next step, we're going to build the print down and the down table. And that's it. Those are my references, and thank you. Any questions?
Okay. Okay. I don't have any questions because I know how this works, more or less. But other people, was it all clear? Hello?
So what's the relationship between the up table and the move structure? It sounds related, and then you also used a Nishimoto-Tabe result at the end, so maybe it's very related, but I was just curious.
So the thing about the Nishimoto and Tabe was that it just guarantees that we're not gonna like flip around the rows. I mean, I have not gone through Nishimura and Tabe theorem yet, but it is just a guarantee to that it's not going to like take a lot of time. And apparently in practice, we don't even need the guarantee because it's not gonna take a lot of time to get us to the predecessor of the J. So that's all I know about it.
Well, also, so it's very it's basically it's Nate's table. What we're doing, the up table is Nate's table for phi, but we're also including the LCP values because MONI-k needs the k. So for each run boundary, it needs the k suffixes with the longest common prefixes with the suffix at the run boundary. And so to find those, we scan up k and scan down k and look at the LCP values. So the move structure doesn't have the LCP values in there. But yeah, it is basically just, it's easy to add the LCP values. So it's the move structure plus LCP. But also it helps us, if we just call it the move structure, it's the move structure for moving up, it's also the move structure for moving down. So I mean, it's just handy to call it the up table and the down table, because otherwise we always have to say the move structure. Which move structure? We've got two of them, especially if we mix it with Nate's stuff, and then we've got like the move structure. What, the move structure for phi? The move structure for phi inverse? The move structure for LF? Which move structure? Yeah. So
yeah.
Yeah, we were thinking about calling it the phi table, but that also leaves out the LCP stuff.
So do you need the whole LCP array? Because that's the one thing that makes this not super practical, right?
Well, it's no. What we need to actually well, actually, wait, Sana,
Yep.
you can answer.
Yeah,
sorry.
I was going to say, let Sana answer. Put yourself on mute,
Okay.
Travis.
Okay, so sorry, just gonna bring the LCP. So you asked that, do we need the whole LCP column?
Yeah, because we don't
Okay.
really know how to build the LCP very efficiently. So
I don't think like there's probably like a way to like we can make it more efficient by just checking if, for example, we're searching if
So well, let's think about this for a little bit.
Yeah.
So where do you actually use the LCP? What do you need from it?
Well, we will need it to see like these like how what is the longest substring between the subs between the suffix arrays that is in common. So I think I don't know if we would not need the LCP.
Well, maybe that's something. No, Travis. Maybe that's something you can think about
Okay.
a little bit after.
Yeah, sure.
To maybe go through your example here
Yeah.
and see where you're using the LCP.
Yeah, sure,
Okay.
definitely.
Remind Susanna, you have you actually in your slides, I remember seeing it when we went through them. You have a note somewhere that, oh, there's stuff in the chat, probably. Oh, okay. No, but you have a note in the slides that you wrote about this is heavy, the structure is heavy,
Yeah.
but you only need it when you build MONI-k.
Yeah, so it was like when we were building MONI-k, it would take of KR, I guess, which said, okay, this is like only for building MONI-k. It's not actually for when we're going to use it for indexing. So that's why it doesn't matter if it's like that heavy.
So
Maybe Travis will let you think about it a little bit on
Yeah.
your own.
okay.
Sure.
And go through an example about where you're using the LCP and where you need it.
Okay, sure.
Yeah. That's the only comment I have.
Can I point out how cute it is that basically this print up, this is phi. Phi is actually like 3 lines long. And one of those lines is just a for loop that's not really doing much. 3 short lines. Wow.
Can I ask other questions, not about related to Sawdust thing?
Okay, but are
I
there
think
other questions?
does anybody have any more questions about Sawdust work?
Should I stop sharing?
Yeah, I think so. I think everyone asked.
Okay, and maybe stop the recording.
Yeah.
So that's